Hey, it's Dr. J. Good morning to you, class. Completing chapter 4 this week. We'll begin with some applications of exponentials and logs. This is going to be part 1 of a 3-part series. Today, we will be learning about compound interest. Let's start with example 1, annual, compounded annually. NNLL, I don't know. So, compounded annually, the formula would be the amount. So A is the amount. That would be the amount after some period of time as a function of time. P is the principal. That's the original amount. It's also known as the y-intercept if we were drawing a graph. Although we're not going to be using the letter y, A is going to act like y. P acts like our old y-intercept from our graphing problems, which we'll do in a minute. T is the time. Typically in years, unless specified otherwise. And R is the annual interest rate. Make sure you write it as a decimal. It's typically given as a percentage, but we'll be converting that into a decimal immediately. So let's suppose you borrow or invest. The same formula can be used in either case. $100 at 3% annual interest. For 5 years. Compounded annually. Then the amount that you would owe after 5 years would be the principal times 1 plus the interest rate raised to the t power. So we have our principal, that's P. We have our interest rate, that's R. And we have our time, that's T. Keep in mind that your interest rate is a decimal, so I like to write it as a fraction first. 3% means 3 divided by 100, percent divided by 100, as a decimal is 0.03. So that's going to be our R. So the amount that we owe, or the amount that we will have in our investment account, is the original P times 1 plus 0.03 raised to the 5th power. So that is 100 times 1.03 to the 5th power. You're definitely going to be needing a calculator for many of these problems. So we got 1.03 raised to the fifth power. So that is 1.15924, etc., and then multiply that by 100. Make sure that you multiply this last. Remember, little brother. Little brother always goes last. So after I have calculated my exponent, then I'm going to multiply by 100, and then we are going to round to the nearest cent. So that is going to be approximately $115. To round to the nearest cent, look at the third decimal place. This is your dictator. Use the 5 or greater rule. That is clearly larger than 5, so we're going to round this up to 93 cents. So after 5 years, if you don't make any payments, assuming it's a loan, or if it's an investment, you don't withdraw any money from your investment account, you should have $115.93 at the end of 1 year. Now, normally at this point I would ask, are there any questions? So I'm just going to assume the question, where does this formula come from? So before we move on to the next example, let me just do a little bit of illustration here to explain where this formula comes from, and then we can move on with some more examples. The key to understanding this is exponential growth is that each year we're applying this factor of 1 plus 0.03, in other words 1.03. This factor happens every year. So you can kind of think of it like this. Year 1, at the end of year 1, assuming this is at the end, you owe $100 times 1.03. That is 1 plus 3%. The 1 represents the original principal plus the interest that you're paying at the end of a year. At the end of year 2, well, you take what you already owed, which was from year 1, and then you multiply it again, and that's what we mean by compounded. The compounding is that you are taking the previous year's debt, carrying it over into the next year, and then adding or multiplying another year's interest. So on and so forth. At the end of year 3, you now have the previous year. I'm intentionally not multiplying these. You take all of the previous year, and then you multiply it one more time, and so on and so forth. Year 4 would be 100 times 1.03 to the 4th power. And then in year 5, at the end of year 5, it would be $100 times 1.03 to the 5th power. So I'm assuming that as we move through this application section, you will just want to sort of memorize the formulas and then apply the principles to each problem that I give you. But I would like to at least give you some understanding of where the formula comes from. So just think of it as a compounding. Each year you're taking the previous year and then multiplying the next year's interest. And so that's the reason why this becomes an exponential equation and not a simple linear equation. We covered linear growth in a previous chapter. This chapter is all about exponential growth. So let's just go ahead and put that in the bank. $115.93. And we have our first formula. So there are various compounding periods. These are represented by n. N you can just think of as the number of compoundings. So if you are compounding annually, then that means n is equal to 1. If you are compounding semi-annually, I could probably be spelling this wrong the whole time. I told you I've got unresolved issues with the word Mississippi, Mississippi, and ever since I was a child, I have always doubled up my letters ANNLL, MMTTSS, and I've never really outgrown that habit. You could compound quarterly, n would be equal to 4. You could compound bi-monthly. That would be n is equal to 6. You could compound monthly. N would be equal to 12. You could compound weekly. N would be 52. Or you could compound daily. N would be 365. We'll give you leap year for free. We don't charge an extra day for leap year. So these are your various compounding periods. There's probably a few more if you really wanted. There's semi-monthly, twice a month. That would be 24. And then there's bi-weekly, every 2 weeks. That would be 26. I did not put any of those periods in the assignments for this section, so I'm only going to give you the ones that I think are necessary for this. If you come across a more exotic example that's not done here, you can simply look up or maybe ask if it's an appropriate number, if your n is the appropriate number. So we have various formulas for this. For annually, we have the amount that you owe is the principal times 1 plus r to the t. For semi-annually, well, semi-annually means every year you cut the interest in half, because you're going to apply half of the interest 6 months in, and then at the end of 6 months, you're going to apply the other half of the interest. So you are going to divide your interest by 2, and then you're going to multiply the time by 2, because every year there are 2 periods in which you are compounding the interest. It's essentially every 6 months they are going to compound the interest. For n equals 4, it's 1 plus r over 4 to the 4t. Easily recognize the pattern here after a few of these, and we will come up with a general formula. You see what's happening? For each compounding period, you divide the interest rate by the number of compounding periods, and then you multiply the time times that number of periods. Finally, or not finally, monthly, 1 plus r over 12 to the 12t. For weekly, 1 plus r over 52 to the 52t. And daily, 1 plus r over 365 to the 365t. In general, all of these formulas give you a formula. A is equal to P times the quantity 1 plus R over N to the N times T. That is your general formula for all the various compounding periods. So take a snapshot of that, put it in your notes, and we're going to be using this formula for the remainder of the problems involving compounded interest. Okay. Let's do an example. I hate to erase all this, but it's got to go. You've got it on your device. So we'll save this formula. We'll save that. We get A equals P, 1 plus R over N to the NT. So let's save that for later. Let's put that in our little cloud. Upload that to the cloud. Example 2. Suppose $500 is invested at 4% per year, 4% interest per year. How much is your investment worth? After 8 years, compounded monthly versus compounded daily. So different compounding periods will give us a different result. And so this example illustrates how we get different amounts based on a different number of compounding periods. Identify who everybody is. You've got your principal, P, got your interest rate, R, and you've got your number of years, T, and then the compoundings are going to tell us what N is. Monthly N is 12, and daily N is 365. So let's start off with the monthly. The amount that we will have in our investment after 8 years is $500 times 1 plus the interest rate, 4%, divided by 12, raised to the 12 times 8 power. You are definitely going to need to have a good calculator for this. Work from the inside out. So we've got 4% divided by 12. That's going to be a repeating decimal. We're going to have to be a little bit careful with that. Let's keep the entire thing on the screen. So 4% divided by 12, and then plus 1 is 1.00, and then an infinite string of 3s. And then multiply our exponent, 12 times 8. Let's try to do that in our head. That's 96. Use your head if you can, because if you clear out your calculator, it's going to be a little bit harder. So we're going to raise this to the 96th power. So that's going to be 500. Remember, wait on the 500. If you multiply the 500 too soon, it's going to screw everything all up. First thing you want to do is do this part first. Multiply the base to the 96th power. I don't know if you can see that on the screen there. That's 1.376395. Don't do any rounding yet until after you've multiplied by 500. Then you can do your rounding. If you try to round it too soon, you'll typically end up with some kind of a mistake. Now we can do our rounding, $688. Look for your dictator. Your dictator is the 7, so that is definitely larger than 5. So we're going to round that up to 20 cents. So we should owe $688.20. Or, I guess I called this an investment, so you imagine this money is sitting in the bank waiting for you. Not too shabby. Yeah, you put $500 in the bank, you're patient for 8 years, you come back 8 years later and you've got $688.20. That's if you don't touch it for 8 years. Alrighty. Let's compare that value with the daily amount now. So, same formula, the amount that we would have would be $500. This time our compounding period is 365. Marley, come down. Come down. Come on. With me. Thank you. I'm back. Apologize. Had to let the dog in before he eats the pool guy. So we got 4% interest divided by 365 raised to the 12. Raised to the 365 because that's our n times 8 years. Now last time I did this in my head. 12 times 8 was 96, and I did that mentally. I don't know about that this time. I don't think I can do that in my head. So let's do that first. Let's just get that over with. 365 times 8. Now, you know, I bought a lot of technological devices and cameras and tripods and whiteboards and things to do this online teaching, but one thing I did not buy is a new calculator. Typical Dr. Jordan. So I'm still using my old, calculator, basic TI-30. If you have a fancier calculator, you can actually type this entire formula into your calculator, press enter, and it gives you an answer. The thing that I don't like about that process is if you make a mistake and you're just typing it in one time, you're going to think that you have the right answer, and there's really no way of sort of retracing your steps. So I'm keeping my old-fashioned simple TI-30 calculator because it just gives me a more hands-on approach. I feel like that at every step, I'm involved in the process and I'm not just, allowing the machine to give me the answer. I mean, of course the machine is assisting me in the answer, but now I know that power should be 2,920. And now I can move on with the problem. So I've got 4% divided by 365. And then plus 1. So that becomes your new base. 1.0001095989 raised to the 2,920th power. So we have 1.377, etc., etc. Remember, keep everything on your screen, multiply it by 500, whatever your principal is in your problem, and then you can do the rounding. 688, 5518. Find your dictator. That's a 1, so we're just going to throw it away. It's smaller than 5. And everything beyond that. So we're going to have approximately $688.55. You can compare the difference. For the first example, we compounded monthly. So you basically, once a month, they compound the interest on your investment. You end up with $688.20. If you switch to daily, all it does is raise your amount by 35 cents. You've got an additional 35 cents by increasing the compounding from once a month to every day of the year, excepting leap years, of course. So that's where all the money goes. Next, we ask a question. What if we compound the interest continuously? Continuously means forever. As many times as nature would allow. Over and over and over again. Every minute of every second. Of every minute, of every hour, of every day. An infinite number of compoundings. What would happen to this formula if we allow the n to approach infinity? And so what happens is the same thing that happened in the previous chapter, in the abstract. As n goes to infinity, the value 1 plus 1 over n to the n, this would be 100% interest. So just as an abstract, 100% interest. We already know, as seen in section 4.2, this value approaches e. the natural exponential. Remember, E is approximately 2.71. I will spare you the details. You can see your notes from 4.2 if you need a refresher on how we evaluated the exponential function for a very, very large number. You might remember it might have been about a month ago, 3 weeks ago, we plugged in 1,000,000, and then we plugged in 1,000,000,000 and 1,000,000,000,000 and so on and so forth until we finally settled on this natural exponential base of 2.71. So what happens is as you compound continuously, that's right, your formula becomes P times E to the RT. So your base changes to E, and your interest rate is multiplied by the exponent RT. So this is your formula. I always remember it as the word PERT. A equals PERT. That's the PERT formula for compounding continuously. This is what we often refer to as the bank of nature. Yeah, you invest in nature, a natural exponential growth function, something like a population of animals or a population of bacteria, or perhaps a radioactive element or something else that occurs naturally would grow according to this continuous growth formula. So, how much is a $700 investment valued at compounded continuously for 3 years at 4.2% per year. Or sometimes they'll say per annum. So, compounded continuously for 3 years. We have our principal, $700. Our time is 3 years. And our interest rate is 0.042. We've got our handy dandy PERT formula here. So the amount is $700 times E to the 0.042 times 3 years, a 3-year investment, or a 3-year loan, however you want to think about it. Remember, make your little brother wait. All right, the 700 goes last. You're going to need a calculator handy. So let's do our exponent first. 4.2% multiplied by 3 years gives us an exponent of 0.126. Find your E button and raise it to that power. 1.13428, etc. Don't round it yet. Multiply by your original $700 investment. And now you have $793.9975. Find your dictator. You get a lot of sevens. So that determines the value. This is a strange one. So the 7 is going to round the 9 to a 10. That's going to round this 9 to a 10. And that's going to round the 3 to a 4. So you're going to have $794.00. The Canvas app is going to require that you enter 2 decimals. So if they both come out to be 0, then enter 0.00 and it should mark it correct. $794. Okay. So we've seen all the important formulas for the financial section. Now we can play around with them a little bit and figure out some investment or borrowing strategies. First thing I want to do is talk a little bit about the values that we have in our formulas. So we have 2 types of compoundings. We have the finite number of compoundings. That's the A equals P times 1 plus R over N to the NT versus the compounded continuous, which is an infinite number of compoundings. Infinite number of compoundings. That is compounded continuously, A equals PERT. But either way, in both cases, we have some vocabulary here. A is called the future value. And P is called the present value. That's kind of neat because P, present, easy to remember, P represents the present value. Sometimes to help you remember this, we could call A the future value or the future amount. How much will you have in the future? You know, because we're not just going to solve these problems in the abstract, we're going to do some financial planning. We'd like to know, if I want to have $5,000 in 10 years, what do I need to do now in order to reach my goal of, $5,000 in 10 years? So example 4, how much should I invest now, that's the present value, to obtain a future value of $5,000 in 10 years if compounded continuously at 9% annual interest. So we're going to use the PERT formula, A equals PERT. And we're going to invest, how much should I invest? That's P. That's going to be our principal or our present value. The future value is $5,000. So the $5,000 now is A. Our time is 10 years, and our interest rate is 9%. So now our formula looks like this. 5,000 equals P times E raised to the 0.09 times 10. Well, this is a one-step problem. I guess there's two steps if you think about this as being a step. First, we want to simplify the exponent. We can do that one in our head. 0.09 multiplied by 10 is just 0.9. So now it becomes just a one-step problem. We're going to divide both sides by e to the 0.9 power. So 5,000 divided by here, let's do it this way. Let's do 0.9. Then we'll do E. So that's going to be 5,000 divided by 2.459603 11111. Getting a little bit sloppy here, but let's just go ahead and rewrite it this way. 5,000 divided by 2.4596031111. This is where having a little bit more expensive calculator might come in handy. 8482999. Look for our dictator. Dictator is 8, so we're going to round this up to a 5. So our answer is approximately $2,032.85. A little bit less than half. Yeah. Pretty good, actually. 9% interest. 10 years is a long time, but if you have a goal, you want to reach your goal in 10 years, you can put aside $2,032.85. Hopefully you can find a bank or an investment broker that'll give you 9% interest. That's quite a stretch, especially these days. I don't know if anybody's been paying attention, but interest rates are way, 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 way down. 9% might have been possible back in the 1980s, but it's probably not possible these days. But nonetheless, it makes for a good math problem. If you invest $2,032.85 at 9% interest for 10 years, the present value is $2,032.85. The future value is $5,000. So this $2,032 now is worth $5,000 in the future. A couple things that are a little bit unrealistic about this. You're not going to get 9% interest. Sorry, it's not going to happen, at least not anytime soon. And you're also not going to find a bank that compounds continuously. So I really just meant this as more of an academic exercise, how to solve for P. In my next example, we can be a little bit more realistic about our values. Example 5, something a little bit more realistic. Suppose you wish to retire. In 20 years. Now you want to have a nice retirement, so you want to have $250,000 upon retirement in 20 years. You can earn 3.5% interest in a retirement account. Those are typically compounded monthly. Yeah, it's a little bit more realistic. 3.5% compounded monthly like a bank would normally do, and you're going to retire in 20 years. And you'd like to have $250,000 to take with you on your retirement afterlife, or what I often refer to as the aftermath. I am about 19, 20, I'm about 20 years into my career now. I'll probably end up putting in 30 by the time I'm done. So let's go ahead and do that. So let's set up our formula. We got A equals P. We're using compounded monthly, so 1 plus R over 12 to the 12t. Remember, this is how much we want to invest now, so we want A, that's our future value. The present value is an unknown value. Our time is 20 years, and our interest rate is 3.5%, which is 3.5 divided by 100, which is 0.035. That's going to be our interest rate. All right, so we've got $250,000. Present value, P, 1 plus 0.035 divided by 12, raised to the 12 times 20 power, and we're going to solve this for P. Let's do a little simplifying before we break into the algebraic steps. Let's just do the arithmetic. So let's see, 0.035 divided by 12 is a very small decimal, plus 1. So 1.00291666666 forever and ever, raised to the 240th power. I went ahead and just did the power in my head. If the power is too big to do mentally, then do it first, unless you have one of the more sophisticated calculators. Okay, so now I'm going to take my base and raise it to the 240th power. So now my coefficient is 2.011702035. Remember, I'm using an old-fashioned calculator, so I'm writing everything down. That's funny that I'm calling this an old-fashioned calculator, but you know what I mean. Standard scientific, it doesn't have any of the fancy buttons on it. So now I'm just going to divide both sides by this coefficient. Again, you could probably just keep that on your screen and do it. I went ahead and cleared it out, but I wrote down the entire decimal, so I've got 250,000 divided by 2.011702035. And my P is $124,272. I'm going to go ahead and round it now because I'm running out of space. And 88 cents. I've already done the rounding for you. You could just look at that decimal and confirm that I rounded it correctly. It's about half. I'd like to compare present value to future value. So $124,000, almost $125,000, is worth $250,000 in 20 years. So it's about half. So that actually brings us to the next question. We've essentially doubled our money. our original principal over a period of 20 years has essentially doubled. You guys see that all the way? You can see the answer. Getting off the screen there, getting a little crooked. So $124,272 essentially doubles to become $250,000. In the next few examples, we want to double our money, or to grow our money. Let's start off with just growing our money, and then we'll go to the doubling problem in a minute. How many years, or how long, will it take for $5,000 to grow to $8,000 if invested at 17% interest compounded daily? So it's not quite doubling, just a growth formula. We're going to go from $5,000 to $8,000, 17%. It's a huge interest rate, and we're going to compound it daily. Let's see how long it takes. How many years are we going to have to wait? To be a little bit accurate, let's round our answers to 4 decimal places. Because it probably will not come out to be a whole number. So we've got our A equals P 1 plus R over 365. Because we're compounding daily. So N is 365. Our principal is 5,000. Our future value is 8,000, and our interest rate is 17/100 or 17%. But our T is the unknown value. So we're solving for T. So we got $8,000 in the future. $5,000 now. 1 plus 17% divided by 365 raised to the 365t. We're going to need a calculator here. Let's see. So 0.17 divided by 365. It's tiny. Plus 1. So we've got 8,000, 5,000, 1.000465753 to the 365t. We're going to break this up step by step. So first, let's divide both sides by 5,000. So we're going to divide 8,000 divided by 5,000. That'll make our base isolated. So we got 8,000 divided by 5,000. I'm sure you could do that in your head, but let's just do it this way. It's going to be 1.6. I did it on my calculator just to be sure, but you probably could have done that 8 divided by 5, right? 8 divided by 5 is 8/5, which is 1.6. All right. Now we're going to use a logarithm. That's the whole lesson that we've been learning lately. So you can use either the common log or the natural log. Let's go ahead and do common log. So I got log 1.6 equals log 1.0046575 to the 365t. Wait to take the logarithms until the very end. So just it's going to be a little bit of writing for a few minutes, but we'll get through it. Bring your exponent down to the front. So you've got log 1.6 equals 365t times log 1.0046575. I actually like to rearrange the order of the 365 and the t. I am really going to run out of space here, so we're going to have to do some Hollywood magic here. Hopefully I'm not losing anybody by doing this. If so, just rewind and watch it carefully. Hopefully you can find where I'm at. That's the problem with these tiny little whiteboards. So I like to rearrange the order. I don't know if you can see that at the bottom of your screen down here. If you can't, I'm going to write it again at the top of the screen. Log 1.6 equals t, and then times 365 log 1.004, etc., 65753. The reason why I'm doing that is because I want my variable and my constants to be separate. So this is the constant, this is the variable. I didn't like having my variable sort of hiding inside the constant down here, if you can see that at the bottom of your screen. So now I've only got one more step, and that's to divide both sides by 365 log of 1.0046573. And again, if you've got a $100 calculator, I don't really know if they're $100, they're just more than $10, which is what I paid for my calculator, then you can probably just type this entire expression into your calculator and get what t is approximately equal to. I'm going to do it in steps. So I'm going to do log of 1.6 just so that you have a way of keeping track of what I'm doing. So log of 1.6 is 0.204119983. That's the numerator. The denominator, I'm going to do log of 1.00465753. So that's the log, and then I'm going to go ahead and multiply it by 365 while I have it on my screen. So now this denominator becomes 0.73658539. So can you keep track of that? The log is what's in black, and the 365 times the log is what's in red. And now I'm going to divide them both. Oh, there's a trick here. I have the 1 over x button, so I can hit 1 over x. That will send this down to the denominator. All right, and then I can multiply that times the numerator, 0.204119983. I got a strange value, so I'm going to double check it. I got 0.2771, which is less than a year. So I'm going to check my answer one more time. I think that's right, but let's go ahead and check. 0.204119983 divided by 0.736585939. Yeah, it confirms. It seems short amount of time. It's a little more than a quarter of a year, so it's about 3 months. Yeah, about 3 months. For the homework, we want all of our answers in the form of a year, so this is a decimal fraction of a year. FYI, this is just for your information. If you want to know how long that is, multiply that by 12, and it would be 3.3 months. A little bit more than 3 months. Okay. Last example. I think this lesson has gone on quite a while. I'm going to do one more example, which is what I alluded to earlier. A very similar type of problem, except for we want our money to double. All right, last example. How long will it take for any investment to double if invested at 10% continuous compounding? So 10% is the only thing we're given, the interest rate. Should be 0.1. %, 10 over 100, 1/10, 0.1. Notice it's any investment to double. So for any investment to double, that means the future amount is equal to twice the principal amount. That's what it means to double. The future is double the principal. So I can plug in, instead of A, my new amount is double the principal. So I don't need the variable A anymore. I have the variable P on both sides of my equation. We can immediately eliminate the P as well by dividing both sides by P. And this would be your doubling formula for continuous compounding. So this will always happen when you're doubling. That's always going to be the case when you are doubling. We're not done with the problem yet. I just was setting it up. So now we're going to solve for t. Solve for t, and let's see what we get. Now, last time I said you had a choice. This time you really do have the same choice, but I think the choice is natural. If you have an exponential e, you're going to use the natural log. So taking the natural log of both sides. If you like to see that step on the right-hand side, you can say ln of e to the 0.1t. You can bring the 0.1t down to the front. Hope I'm not getting off the screen here. And you have the ln of e is 1. So now you have ln of 2 is equal to 0.1t. The ln of e is just 1. Oftentimes people will just go like this. They'll just cancel off the ln and the e and just bring down the 0.1t to the right-hand side. Divide both sides by 0.1, 1/10. So now you have ln of 2 divided by 0.1, or 10 times the ln of 2. These mean the same thing. If you don't believe me, do it. ln of 2 times 10. That comes out to be 6.9315. I'm rounding. It's approximately 7 years. You can also do it this way. ln of 2 divided by 0.1, and you still get the same value, 6.9315. For your homework, why don't you go ahead and just enter 6.9315, but keep in mind that it's about 7 years. This is sometimes called the continuous growth rule of thumb. 10% interest, it takes approximately 7 years to double your money. An interesting fun fact is you can reverse the 10 and the 7. So here's a neat fun fact. If it is 7% interest, then the number of years changes to 10 years. And that's your fun fact for the day. Okay, Math 10 students, that was a little over an hour. It's my longest lecture yet. This was just part one of a 3-part series. I'm going to be posting a quiz on Canvas later today. Don't worry, I'm not putting any word problems on the quiz this week. The quiz this week is based on the lecture from last week. So just solving the exponential equations. Cheers. Oh, and logarithmic equations as well. But no applications this week. I'll save the applications for the Chapter 4 test, which will be coming next. Soon. Whatever that means in this new internet age. Okay, until then, I'll see you on the internet.